Hello everyone, I'm Wei with the students from mathematics department, and the main goal of this presentation is to discuss about Riemann integration. And actually, the most important result for integration is from the fundamental theorem of calculus, which states that the integration and differentiation are inverse operations in an appropriately understood sense. This connection enables us to compute many integrals explicitly. And integrability is a less restrictive condition on function than differentiability. Generally speaking, integration makes functions smoother while differentiation makes function rougher. For example, the indefinite integral of every continuous function exists and is differentiable, whereas the derivative of continuous functions need not to exist and typically does not exist. The Riemann integral is actually the simplest integral to define, and it allows us to integrate every continuous function as well as some not to valid discontinuous functions. So in this presentation, I would like to discuss about one question about this Riemann integral. And without wasting time, we now move on to the question one. Suppose that the function of domain 0 to 1 is Riemann integrable, so that the Riemann integral of f from 0 to 1 is equal to the limits from n to infinity 1 over n multiply with the summation from k equal 1 to n f k over n. So in order to prove that the statement is true, we have to show that for all epsilon greater 0, there's an big N, which is an integer not equal to 0 such that the absolute value of the difference between this summation of fk over n from k equal 1 to n multiplied 1 over n is, and the integral of f from 0 to 1 is less than epsilon for all small n greater than equal to big N. So now we start with our proof. Let P be the partition of the interval between 0 and 1. And since f is a Riemann integrable function on the interval 0 to 1, then we know that for every epsilon greater than 0, there exists an delta greater than 0 such that for any p with non-p less than delta, we have the upper double sums minus lower double sums is less than epsilon. And this non-p is actually the maximum length of the intervals in the p. So we need to make sure that the non-p is less than the delta. Now we let Pn be the sequence of regular partition of the interval 0 to 1, which divide the partition P into n subintervals of equal length 1 over n. That is, Pn is the sequence is equal to the sequence from 0, 1 over n, 2 over n, and it continues until 1. And now clearly, if big N is an integer such that big N is greater than 1 over delta, then for any n greater and equal to big N, we have the non-Pn less than delta. And we will have the difference between the upper double sums and the lower double sum is less than epsilon. Now we set the mk, small mk be the infimum of fx, where x is in the interval between x k minus 1 to xk, and big mk be the supremum of fx, such that x is in xk minus 1 to xk. And we will have the lower double sums, which is also equal to the summation of mk multiplied with xk minus xk1 from k equal to 1 and to n. Then, from just the above slide, we know that the difference, the Pn is divided into n subintervals, and the difference between the xk and the xk minus 1 is 1 over n. And now we can substitute the 1 over n into this equation, and then we will have the lower double sums be the summation of k equal 1 to n mk1 over n. And similarly, we will have the upper double sum, which is equal to the summation from k equal 1 to n big mk xk minus xk minus 1, which is equal to 1 over n, and we will get the summation from k equal 1 to n big mk 1 over n. And now, since f is a Riemann integral function, and from the definition of integrability, we know that the integral of x from 0 to 1 is equal to the lower integral as well as the upper integral. Then we also know that the integral of f from 0 to 1 is actually greater and equal to the lower double sums and less than equal to the upper double sums. Then we know that the difference of the upper double sum and the upper integral is less than equal to the difference between upper double sum and the lower double sums, and also greater and equal to 0. And from just now, we have said that the difference between the upper double sum and lower double sum is less than epsilon, and hence we will get the summation of k equal 1 to m big mk or 1 over n, and the minus the upper integral is less than epsilon, and as well as greater than equal to 0, and we will form this equation 1. So same and similarly, the lower integral, which is the supremum of the lower double sums minus the lower double sums, is less than equal to the difference between the upper double sum and the lower double sums, and is greater than equal to 0. And from above, we also know that this difference between, we have defined that the difference between upper double sum and the lower double sum is less than epsilon, and we will form this equation 2 such that the lower integral minus the summation from k equal 1 to n, small mk 1 over n is less than epsilon. And since small mk is less than equal to fk over n, less than equal to big mk, and we will have these equation trees such that the summation of k equals to 1 to n fk over n 1 over n is less than equal to the summation of big mk 1 over n from k equal 1 to n, and is greater than equal to the summation from k equal to 1 to n mk 1 over n. So how can we form this equality? And from the slide above, we know that this mk is the infimum of fx for the x in between the interval xk minus 1 to xk, while the big mk is the supremum of the function of fx from in the interval for x in the interval xk minus 1 to xk. Then if we define any function fx where the x is k over n such that the k over n is between the interval xk minus 1 to sk. Actually, this k over n is less than equal to its supremum value and greater than equal to the infimum value. By combining the equation 3 with equation 1 and 2, we obtain the absolute value of the difference between 1 over n. Summation from k equal 1 to n, fk over n, and the integral of f from 0 to 1 is actually less than epsilon for all n greater and equal to big N. So by using the definition of convergence, we know that the limits of n to infinity, 1 over n multiplied with the summation of k equal 1 to n, fk over n, is equal to the integral of fx from 0 and 1. So, and we finally prove that the statement is true. So, that's all for my presentation, and I hope that you will have a better understanding about double sums and the Riemann integral and some other knowledge related like convergence of a function, limits of function, uniform continuity, and others. So I would like to stop at here and everyone stay home and stay safe. Bye.